So from the previous videos, we now know what the ring of regular functions is on these distinguished open sets. And now in this short video, we want to see an example what this ring is for a set U which is not of this form. And the example is the one that we have already alluded to before, namely we take A2 minus the origin inside A2 and try to compute what the functions are there. So here's A2, here's the origin, we remove it. We want to understand the functions here. And the claim of this example is that this ring of functions is just given by the set of polynomial functions, which is the same ring of functions as the entire thing, A2. So in a certain sense, this is a bit disappointing because it shows that, removing this one point doesn't really change the set of functions. Or, in other words, if you have any regular function on U, then it actually extends over this point, because secretly it's a restriction of a function from all of A2. And that behavior is very similar to some theorems from, again, complex analysis, like the removable singularity theorem, or sometimes called Hartog's theorems, which says that every holomorphic function on C2 minus the origin can be extended holomorphically to all of C2. So in a certain sense, this point that we remove is too small to create any difficulty for the function to extend. And to show it, well, we observe that U has this cover by dx1 union dx2 that we have already seen before. And if you have any function on U, then it of course restricts, or the regular function on U, then it restricts the regular functions here. So in other words, phi restricted to dxi is a regular function on this distinguished open set. But this now we understand perfectly. And so this means this is the localization of all functions on all of A2 at the element xi. So in other words, phi is given by f divided by x1 to the m on dx1, and as some possibly other representation, g divided by x2 to the n on dx2, where these are polynomials. And basically, we want to show that there cannot really be any denominator appearing. And to do that, well, we just start manipulating this representation. So first of all, you can assume that x1 does not divide f, because otherwise you kind of just divide both numerator and denominator by x1, you still get a valid representation. And similar here. And then, well, you just observe this happens on dx1, this happens on dx2. But so in particular, if you remove both of those things, so it's kind of here in this region, these two functions are both valid representations of phi, so they agree there. So we have this equality here in the ring of functions on dx1 intersected dx2. But now, maybe this rings a bell because we have seen that the intersection of these distinguished open sets is just distinguished open set of the product of the two functions. But here, this thing, this ring, we have identified in the last video just as the localization of the polynomial ring at this element here. Okay, so we do see that we have this equality not just kind of as functions, but actually in this particular localization. And so by definition of localization, this equality just means that after clearing denominators and multiplying by some power of the thing we localized at, this difference here becomes 0. And now we could have spared ourselves this term because this is the domain, you can always kind of get rid of this term here. Because this product is 0 if and only if one of the factors is 0. So since this is non-zero, you can just strike it out. So we really have this equality here in the ring of polynomials. And now, well, this is a very nice ring because it's a unique factorization domain. And so we want to show that these the denominators are actually 1. So we want to show m is equal to 0 and n is equal to 0. So assume m was non-zero. Then this product here would have a factor x1. So this would mean x1 divides, of course, this side, and so it also divides this side. But now, well, x1 is a prime element in this thing because, and this is where I really use the UFD, it's very easy to see that x1 is an irreducible element, right? Because of degree reasons, it just, it cannot be decomposed as the product of two non-units. So it's irreducible. Because this ring is a UFD, this implies that it's actually a prime element. And this prime element x1 would then divide this product, but by our assumption, x1 does not divide f. And it's also pretty clear that x1 does not divide x2. And that would give us a contradiction. And so it cannot be that m is greater than 0, so m is 0. And by the similar argument, n is 0. And so phi is just given by f divided by 1. It's also given by g divided by 1. So all of these things agree, and in particular, f and g were elements in this ring. So phi comes from this ring, which is exactly what we want to show here. And that concludes the proof. So we have seen in this special case, if you remove just a single point inside A2, it doesn't change the regular functions. And this can be generalized, and that is kind of an exercise. So assume that Y is a non-empty irreducible subvariety of some affine variety X, and U is the complement. Above, we looked at the affine variety X equals A2, and Y is just this origin. Then two parts. First, assume that we have this UFD condition, which we already used before. Assume that this is an UFT, then the claim is the ring of functions on U equals the entire ring of functions, if and only if the codimension of Y is at least 2. That's certainly the case here because, well, the dimension of a single point is 0. It sits inside a two-dimensional space, so the codimension is 2. And so this explains somehow this part A would also apply to the special case, which we did by hand. And the interesting thing is that this is an if and only if. And I think this is a great exercise because it brings together a lot of things from the previous sections also, if you actually try it. The slogan for this part A that you might remember is that at least on nice spaces, like spaces whose ring of functions is UFD, regular functions extend over sets of codimension at least 2. So if you just remember one slogan from the video, that should be it. And part B, well, you try to come up with an example where A is false without the UFD assumption. So in particular, you need an X such that AX is not a UFD, and you might go back in the lecture and see if something comes up. Okay, so that was showing that regular functions extend over sets of codimension at least 2, at least on spaces which are nice enough.